So if the graph of f of x passes the horizontal line test, then f inverse of x is a function. So in our example, f of x is 1/5 x cubed minus 2, and it graphs this wiggle through the y-axis at -2. Then it passes the vertical line test, which makes it a function. It passes the horizontal line test, which means its inverse will also be a function. And f of x is said to be 1-to-1 if its inverse is also a function. Okay, if you turn to the back of the notes in example 4, if the graph of f of x passes the VLT, vertical line test, then it's a function. If it passes the HLT, the horizontal line test, then the inverse is also a function. And both must be true for it to be 1-to-1. So pause the video and look at A, B, and C and determine whether those graphs are 1-to-1. So in example 1, -3x plus 5/2 passes both the vertical and the horizontal line test. So this is 1-to-1. In example B, the graph of the parabola, the quantity x minus 1 squared plus 2, passes the vertical line test but fails the horizontal line test. And so this is not 1-to-1. In C, 1/2 x cubed minus 1, the graph passes both the vertical and the horizontal line tests, so this function is 1-to-1. For this cube root example, we're going to use the graphing calculator in order to determine whether the function is 1-to-1. And the screenshots in the notes are from the TI-84 Plus Silver Edition that we use in class. The emulator that I'm using here is a TI-83. They're similar in function, but the notation may appear different. For instance, in the y equals, when we type in 2 times the cube root, we go to the math function and arrow down to number 4. And then x and close the parentheses and a plus 2. So if you compare the TI-83 screenshot, oh, we need another parentheses. Okay, compare the TI-83 screenshot to the TI-84 screenshot, you can see how this cube root notation is different in the newer calculator model, but the functions will be the same. Okay, next we're going to go to the graph, and that's the last blue button on the right under the screen. Okay, then we're going to hit trace, and this allows us to type in a value for x, press enter, and it'll tell us the corresponding y for the function that's shown in the top of the screen. And this function is what we typed in for y1. So I'm going to put in a 0 for the x, press enter, and there you see that y is equal to 2. That gives me a point that I can plot on my graph. So I'll come over to my x-axis and put in 0, 2, and that's the y-intercept. Okay, then to see more points, we could continue typing in numbers for x, or you can see all of your ordered pairs going by integers by pressing this yellow second button and then the graph button again, and that reveals the table. You can use the up and down arrows to show positive and negative values, and we're looking for whole number values, so -1, 0, 0, 2, and 1, 4 would all be whole number values that we can use to sketch the graph of the function. So -1, 0 is the x-intercept, 0, 2 is the y-intercept, and then 1, 4. And that wiggle shape comes through these 3 anchor points and then off to positive infinity. Okay, in example 1, the table on the left shows x and the output f of x, and then the table on the right is the x's and the output for f inverse of x. If xy is a point on the function, then we reverse the coordinates to get the point y comma x on its inverse. So as you can see from the top row, -7, -31 on the function becomes -31, -7 on the graph of the inverse. So if -3, -9 is a point on the function, -9, -3 would be on the inverse. If 1 is a y value for the inverse, then its corresponding x value in the function is 1. Similarly, if -15 is a y value for the function, then on its inverse, the x value will be -15. So same thing for these last two rows. This would be 5, 17 and 17, 5, 9, 33 and 33, 9, because all of the x, y coordinates for the function f of x have to be reversed in position to become y, x on the graph of its inverse. When we're looking at the graphs of f of x and its inverse, they have symmetry about the line y equals x, and that's the dashed diagonal green line that goes through 0, 0, and 1, 1 on the coordinate plane. So if the graph of the function f of x has the point -3, 1, we switch the x and the y to get the point 1, -3 on the inverse. If the graph has a point 3, -3 on f of x, then we're going to switch the x and y and go to -3, +3 for the graph of the inverse. And then where the line y equals x intersects with f of x, that will always be a point that they share. So we can see along that line of symmetry, if we fold the paper in half, these two curves for f of x and its inverse would lie on top of each other. They create a mirror image going across that line of symmetry. So you can pause the video and try these two examples on your whiteboard. You want to use the ordered pairs for the function f of x in order to create its missing values in the inverse. So when we look at f of x, the point -5, 8 and 8, -5. Then we have the point -4, 5, and on the inverse 5, -4. For the 4, -1 on the inverse, that becomes -1, -4, and then -2, -1 on the function becomes -1 and -2. One that's a little trickier through the middle here, we can discern from the pattern in the x's. So -5, -4, the next would be -3, -2, -1, and the corresponding y value then is -3. If we look in the pattern for the outputs for f of x, 8 minus 3 is 5, 5 minus 3 would be 2, 2 minus 3 is -1, 1 minus 3 is -4, and so its corresponding x value for the inverse would be 2.